Tonight, we're going to drift through one of Earth's quietest mysteries, the rhythm of the ice ages. About every 100,000 years, give or take, our planet tends to slide into long, cold chapters. When glaciers expand, sea levels fall, and entire landscapes change their shape. But Earth doesn't freeze on a schedule like a clock. The timing is real, yet the reason is subtle. It's written in slow motions, the stretch of our orbit, the tilt of our axis, the wobble of our spin, and the way ice, oceans, and carbon dioxide respond, sometimes gradually, sometimes all at once. So get comfortable, let your shoulders soften. And as we move through the chapters ahead, imagine you're watching the planet breathe in deep, ancient cycles over the calm, patient span of time. Imagine Earth from far away, as if you're watching it from a quiet distance, a small, luminous sphere turning slowly in the dark. From here, everything looks steady. The sun rises, the sun sets, seasons come and go. Winters feel cold, summers feel warm. It all seems predictable, almost permanent. But if you keep watching, if you allow your viewpoint to stretch beyond days, beyond years, beyond even human lifetimes, you begin to notice something softer, slower, and strangely beautiful. The predictability is real, but it's layered. Under the familiar rhythm of day and night, there is another rhythm, and under that, another still. A set of deep, gentle motions that Earth performs as it travels around the sun. These motions are not dramatic. They don't feel like events. They feel like background, like breathing, like the slow settling of snow in a forest where no one is walking. And yet, over very long spans of time, these small motions change how sunlight arrives on Earth, where it lands most strongly, where it arrives more faintly, and how that light is distributed across seasons and latitudes. Not enough to matter much from one summer to the next, but enough to matter enormously when thousands of summers stack on top of each other, one after another, in a long, quiet pile. It can help to think of sunlight not as a constant, but as a pattern. The total energy Earth receives from the sun is fairly steady compared with the day-to-day weather chaos we experience on the surface. But the way that energy is spread out across the year, across the globe, can shift, and climate is deeply sensitive to distribution, to timing, to whether a region receives its strongest warmth at the right moment to melt snow, or whether that warmth arrives slightly reduced, slightly late, slightly misplaced, year after year. There are 3 slow motions, 3 long cycles, that work together to rearrange sunlight like a careful hand moving a lamp around a room. None of them is responsible for every detail of an ice age by itself, but together they create a kind of celestial choreography that nudges Earth toward warmer or colder patterns, depending on how they line up. The first motion is about the shape of Earth's path around the sun. We often picture Earth's orbit as a neat circle, like a ring. But in reality, it's a little more like an oval, and that ovalness isn't fixed. Over long spans of time, Earth's orbit slowly changes shape, becoming slightly more circular for a while, then slightly more elongated, then easing back again. This is called eccentricity. It's a measure of how stretched the orbit is. When the orbit is closer to circular, Earth stays at nearly the same distance from the Sun all year. When the orbit becomes more elongated, there is a bigger difference between Earth's closest approach to the Sun and its farthest point away. Even when the orbit is more elongated, the change in distance is still not enormous, and the change in total annual sunlight received by Earth isn't the main story. The deeper story is that eccentricity changes the stage on which the other motions perform. It can make seasonal contrasts stronger or weaker, not directly like a switch, but indirectly, like adjusting the sensitivity of a dial. Because when Earth is slightly closer to the sun, the sunlight is a bit stronger, and when Earth is slightly farther, it's a bit weaker. So if the timing of seasons happens to place summer in one hemisphere, at the closer part of the orbit during a time of higher eccentricity, that hemisphere can receive a somewhat more intense summer. If summer aligns with the farther part, it can receive a somewhat milder summer, and that mildness matters in a way that's easy to underestimate. Because the growth of ice sheets is not only about how cold winters are, it's about whether snow and ice survive the warmth. Winter can create snow almost anywhere with the right conditions, but summer decides what remains. So eccentricity, quietly stretching and relaxing the orbit over long cycles, influences how dramatic the seasonal light differences can become when combined with the other motions. It sets a kind of background tempo, a slow, steady pulse in the geometry of Earth's journey. The second motion is about Earth's tilt. If you imagine Earth as a spinning top, you can picture the axis, the invisible line running through the planet from the North Pole to the South Pole. That axis is not perfectly upright relative to the plane of Earth's orbit. It leans, and that lean is the reason we have seasons. When the northern hemisphere is tilted toward the sun, it experiences summer. When it's tilted away, it experiences winter. The southern hemisphere experiences the opposite at the same time. What's easy to miss is that Earth's tilt is not constant. Over long periods, it gently changes. Sometimes the planet stands a little straighter, with a slightly smaller tilt. Sometimes it leans a bit more. This change happens slowly, so slowly that it doesn't feel like change at all within a human lifetime. But over tens of thousands of years, the difference matters because tilt controls how strongly the seasons contrast. A larger tilt means stronger seasons. It gives high latitudes more intense sunlight in summer and less sunlight in winter. Summers become warmer and winters become colder, especially closer to the poles. A smaller tilt softens the seasons. It brings summers that aren't quite as warm and winters that aren't quite as dark and severe. The contrast fades a little, like the volume of the seasonal cycle has been turned down. And again, that softening, especially of summer warmth at high latitudes, can be very important for ice. If summers are intense, they melt snow and ice efficiently. They erase the winter's work. But if summers are slightly cooler, snow can linger. A little patch of snow that might have melted completely in a warmer summer can survive. First as a stubborn remnant, then as something more permanent, growing thicker as more snow accumulates on top of it each winter. The planet does not need to become dramatically colder everywhere for this process to begin. It only needs certain key regions, especially in the far north, to receive just a bit less summer energy for long enough that melting can't keep up with accumulation. So tilt is like a gentle hand controlling how sharp the seasonal knife edge is. It decides how much summer can cut into winter's buildup. The third motion is perhaps the most dreamlike, the wobble. Earth spins, and like a spinning top, it doesn't stay perfectly stable. Its axis slowly traces a circle in space, a gradual wobble called precession. If you've ever watched a top wobble as it spins on the floor, you've seen a fast, obvious version of this. Earth's version is far slower and far calmer. One full wobble takes many thousands of years, but this wobble changes something subtle and important. It changes which part of Earth's orbit lines up with which season. Remember that Earth's orbit is slightly oval, and Earth is sometimes a bit closer to the Sun and sometimes a bit farther away. Precession shifts the calendar relative to those orbital positions. Over time, it moves the timing so that summer in a given hemisphere might occur when Earth is closer to the Sun, and at other times summer occurs when Earth is farther away. This can strengthen or weaken seasonal differences in that hemisphere. If Northern Hemisphere summer happens when Earth is closer to the Sun, summers there tend to be somewhat warmer and winters somewhat milder. If Northern Hemisphere summer happens when Earth is farther away, summers tend to be somewhat cooler and winters somewhat harsher. But for ice sheets, the key is not harsher winter. It's the coolness of summer. If summer energy weakens in the north, snow survives. And surviving snow is the beginning of a long memory, because snow reflects sunlight, and reflected sunlight reduces warming, and reduced warming helps more snow survive. Precession is the cycle that most directly shifts the seasonal when of sunlight. It's about timing, like changing the hour when a lamp turns on in a room. The light is still the light, but if it arrives at a different moment, if it arrives when the room is already warm, or when it's still cool, it can change what happens next. Now something important happens when you look at these three motions together. They do not act like independent knobs that you adjust one at a time. They overlap, they interfere, they sometimes reinforce each other and sometimes cancel each other out. Climate responds not to any single motion in isolation, but to the combined pattern of sunlight distribution that results. It's like three slow waves crossing each other on the surface of an ocean. Sometimes they align and create a larger swell. Sometimes they oppose and flatten the surface. The ocean is still the ocean, but the pattern of motion changes. In the case of ice ages, one of the most important outcomes of these combined cycles is what happens to summer sunlight in the high northern latitudes. You can picture a place like northern Canada, or Scandinavia, or Siberia, regions where winter is long and snowfall can accumulate. These regions matter because they have large areas of land where ice can sit and grow. Land holds ice sheets. It gives them a platform. The decisive question is almost tender in its simplicity. When summer arrives, does it melt most of the winter snow? Or does enough snow survive to carry over into the next year? If most of the snow melts each summer, then winter snow is like a temporary blanket. It comes and goes. It has no long memory. But if even a small fraction survives year after year, if the summers are just cool enough, just mild enough, just short of the melting threshold, then snow begins to persist. Over time, persistent snow compresses into ice. Ice thickens, and once it's thick enough, it becomes harder to melt, because thick ice can hold on to cold like a deep cellar. The process begins almost invisibly, as if the planet is making a quiet choice. At first, it might look like nothing more than patches of snow lingering in shaded valleys, on high ground, in places where the sun's angle is low. But over centuries, these patches can expand, they can connect, they can become small glaciers. Glaciers creep outward inch by inch, year by year, reshaping the land. And while all this is happening, the planet's reflectivity increases. Snow and ice reflect sunlight. darker surfaces like forests and oceans absorb it. So as snow and ice expand, more sunlight is bounced back into space. Less energy is absorbed. The region cools further. That cooling encourages more snow to survive. A feedback loop begins. Not a fast, violent loop, but a patient one. This is why, in the language of ice ages, summer is often more important than winter. Winter can pile snow on the surface, but summer decides whether that snow becomes part of a long-term ice sheet or whether it disappears. This is also why small changes in sunlight can matter, because the system has thresholds. There is a difference between a summer that melts 99% of winter snow and a summer that melts 95%. That difference sounds small, but over many thousands of years, it can mean the difference between nothing accumulates and ice slowly builds. And the orbital cycles are exactly the kind of forces that can produce persistent, long-lasting nudges. Nudges that don't need to be large, only steady. It can also help to remember that these cycles do not directly control temperature the way a thermostat does. They control insolation, solar radiation reaching specific places at specific times of year. A common misconception is that an ice age happens when Earth receives less sunlight overall. But often, the more relevant detail is that certain regions receive less summer sunlight, even if the global annual average doesn't change much. Climate is not only about totals, it's about patterns, about where heat is concentrated and when it is delivered. A mild northern summer can allow ice to survive and grow. Once large ice sheets exist, they begin to influence the world around them. They can shift winds, alter storm tracks, and affect ocean circulation. But those are later chapters in the story. Right now, in this slow beginning, we're simply watching the gentle steering of light. And it's strangely calming to realize that the sun itself hasn't changed dramatically to create these swings. Instead, Earth's own movements, its slow tilt adjustments, its wobble, the quiet reshaping of its orbit, alter how the sun's energy is spent across the planet. You could think of it like Earth changing the way it angles its face toward the warmth. A slightly different tilt, and the northern summer becomes a little less capable of clearing away winter's snow. A slightly different wobble, and summer occurs when Earth is a bit farther from the sun, softening the warmth when it matters most. A slowly changing orbit, and the strength of that wobble's effect rises and falls over long periods, as if the seasonal differences are being gently modulated. These motions, in combination, can bring the planet to moments where the northern summer is persistently mild for thousands of years. Mild enough that snow remains, mild enough that glaciers don't retreat fully, mild enough that the bright reflective surface of ice expands and begins to cool the region further. And if you let your mind rest on that idea, on the quiet persistence of small causes, it can feel almost like listening to a lullaby sung by geometry. Nothing abrupt, nothing hurried, just a world turning and leaning and wobbling while circling the sun. It also helps to remember that while these orbital cycles are steady, their climate impact can feel irregular because Earth's climate system has its own complexity. The same amount of sunlight change can have different results depending on what the oceans are doing, how much carbon dioxide is in the air, where existing ice already lies, and how reflective the surface of the planet is at that time. But the orbital motions provide the rhythm. They provide the repeating invitations. Sometimes Earth's internal systems respond strongly. Sometimes they respond gently. But the invitations continue, cycling through their slow patterns, returning again and again. And so, in this first part of the story, the central idea is simple and comforting. Over long spans of time, Earth's orbit, tilt, and wobble subtly rearrange sunlight. Those changes are especially important in the high northern latitudes, where summer melting determines whether winter snow disappears or becomes the seed of long-lasting ice. And when summer sunlight weakens enough, persistently, patiently, snow can survive. Ice can grow, and the planet can begin, almost quietly, to lean toward an ice age. So as you settle deeper into rest, you might imagine those three motions continuing in the background, so slow they feel like stillness. A path around the sun that gently stretches and relaxes, a tilt that subtly shifts, a wobble that changes the timing of seasons like a drifting clock hand, and over it all, the steady glow of sunlight, arriving year after year, in patterns that are never exactly the same, yet always part of a larger, repeating dance. Now, let your attention drift northward, toward the top of the world, where the map narrows into quiet, pale latitudes, places where winter arrives gently at first, then stays, where the sun, in the cold season, can feel like a memory, and where, when it finally returns, it returns at a low angle, slanting across long shadows, glinting on frozen lakes, and touching the land with a light that is beautiful, but not always strong enough to undo what winter has built. To understand why ice ages become global stories, it helps to begin with something surprisingly local. Not the whole Earth at once, but a specific question, asked in a specific region over and over again. When summer comes to the far north, does the winter's snow completely disappear? Because for the great ice sheets to grow, snow can't be temporary. It has to become a habit. It has to remain. Just a little, from one year to the next, and then a little more, and then more still. It sounds almost too simple, but the truth is gentle like that. Huge outcomes can begin with small imbalances. In many northern landscapes, winter snow is generous. Storm after storm arrives, dropping fresh layers, smoothing the ground into silence. The cold keeps it from melting. The nights are long. The air is still. It's easy, in such conditions, for snow to accumulate. But winter alone doesn't create an ice age. If summers are strong enough, they erase winter completely. Snow becomes a seasonal visitor, here for a while, then gone. The land returns to darker colors, soil, rock, forests, water, and those darker surfaces drink in sunlight, warming the region efficiently. So the turning point is not simply more snow. The turning point is less summer melt. In the high northern latitudes, summer is the great test. Summer is the season that decides whether snow becomes history or whether it becomes memory. And when snow survives summer, even in thin remnants, the physics of the surface begins to change in a way that feels almost magical, but is actually very precise. Snow is bright. Ice is bright. They reflect a large portion of incoming sunlight back into space. This reflectivity is called albedo, and you can imagine it like this. A bright surface is a mirror for heat, while a dark surface is a sponge. A forest canopy, dark soil, open ocean. These absorb sunlight. They warm. They help melt any nearby snow. They encourage more warming, but snow and ice do the opposite. They refuse the heat. They send it away. And in doing so, they keep themselves colder. A cold surface is good at staying cold. So if a region gains even a little extra snow that persists, it becomes slightly brighter, slightly more reflective. It absorbs slightly less sunlight. It warms slightly less. That means the next summer has a harder time melting what's there. And if the next winter brings more snow, as winters usually do in those latitudes, then the pile grows. It isn't an explosion. It's a slow, patient compounding. This is why ice ages don't begin with a cinematic freeze across the globe. They begin with persistence. With summers that are mild enough, often repeatedly mild enough, that winter's work is not fully undone. Over time, persistent snow undergoes a quiet transformation. Fresh snow is fluffy. It holds air. It sparkles. But when it remains through seasons, it compresses. Each new snowfall adds weight. The lower layers compact into grains, then denser pellets, then something closer to solid. This compressed snow is called firn, a transitional state. And when firn continues to compress, it becomes glacial ice. Glacial ice is not just snow that got old, it's snow that became pressure, snow that became time. And once ice exists in thickness, once it becomes more than a thin crust, another kind of memory appears. Thick ice is harder to melt because the surface can melt, while the deeper layers remain cold and intact. Like a deep cellar that holds onto winter even when the air outside has warmed. Then the ice begins to move. Ice sheets and glaciers don't sit still forever. Under their own weight, they flow, slowly, silently, like a very thick liquid. They creep downhill, they spread outward, they grind the landscape, they reshape valleys. But again, all of this begins with the same fragile requirement. Summer must fail by just enough, year after year. And now, we arrive at the question of why the North is so central to the story. The Northern Hemisphere has something the Southern Hemisphere mostly lacks: enormous land, areas at high latitudes, Canada, Alaska, Greenland, Northern Europe, Siberia, vast connected stretches where snow can accumulate on land and remain on land. Land is a platform. It holds ice in place, allowing it to thicken. It gives the ice sheet an anchor, a foundation on which it can grow upward and outward. The Southern Hemisphere, meanwhile, is dominated by ocean at comparable latitudes. Antarctica is its own immense ice world, isolated by currents and winds, already cold and high. But outside of that, the southern high latitudes are mostly water, and water behaves differently. Ocean mixes heat. Ocean circulates. Ocean resists building the same kind of sprawling continental ice sheets that can cover millions of square kilometers of land. So the North becomes the main stage, the place where the Ice Age drama can scale up. And it's not only because of land, it's also because of the way sunlight arrives there. In northern summers, the sun can remain in the sky for very long hours, hovering low but constant, sometimes barely setting. The day can be endless, which means summer sunlight is concentrated not into brief, intense bursts, but into long, slow exposure. When orbital cycles reduce that summer exposure, when they slightly lower how much energy reaches northern land during the crucial melt season, snow survival becomes more likely. And once survival begins, feedbacks take over. There is also a subtle geographic advantage for ice growth. Much of the northern land that matters lies at elevations and latitudes, where small temperature changes strongly affect whether precipitation falls as rain or snow, and whether snow lasts. In other words, these regions sit close to the threshold, and thresholds are where small nudges matter most. Now, imagine the planet entering a phase where northern summers are repeatedly modest, not catastrophically cold, just not quite warm enough. The first change might be small. Snow patches linger into late summer in shaded places. Mountain glaciers retreat less than usual. Some winters add more snow than the summers remove. And then, over centuries, the snow line, the altitude and latitude where snow can survive year-round, shifts. As that snow line shifts, the surface brightens. More reflection, more cooling, more snow survival. A gentle loop tightens. The cooling doesn't stay perfectly local either. As ice sheets begin to expand, they influence winds. They influence storm tracks. They can push the jet stream into new patterns. They can change how moisture travels, which changes where snow falls. They can, over time, influence oceans as well by affecting freshwater input and sea level. But even before all of that becomes dramatic, the simple truth remains. The North is the ignition point because it has land, it has long summer days, and it sits near crucial thresholds of melt. And because ice is not just a passive result of climate, ice is an active participant. As ice grows, it cools the region by reflecting sunlight. And that cooling is an invitation for more ice. So the planet, once it begins leaning toward glaciation, can reinforce its own movement. This is why the idea of an ice age can feel so immense, because it is. But its beginnings are quiet. They start as an imbalance in the seasonal bookkeeping. Slightly more snow added than removed. And now, with that calm foundation, we can move into a mystery that has fascinated climate scientists for decades. One that feels almost like a riddle whispered by the heavens. Because if you look at the orbital cycles that influence sunlight, one of them stands out as a clear and powerful player, Earth's tilt, which cycles over about 41,000 years. Tilt changes the intensity of high-latitude summers in a very direct way. You'd expect it to leave a strong signature in the timing of ice ages, and it does, especially deeper in the past. But when you look at the pattern of major ice ages over the last several 100,000 years, another rhythm emerges, one that seems to dominate, a cycle closer to 100,000 years. And that is strange, because the orbital factor that has a roughly 100,000-year rhythm, eccentricity, the stretching and relaxing of Earth's orbit, does not, by itself, change Earth's total sunlight very much. Its direct effect on global annual energy is relatively subtle. So why do the largest, most dramatic ice age cycles often seem to follow that slower beat? This question is so well known that it has a nickname, the 100,000-year problem. It's not a problem in the sense that it breaks physics. It's a problem in the sense that the simple explanation, eccentricity causes ice ages, doesn't fully satisfy. The climate response looks larger than the direct orbital forcing seems to warrant. So the mind naturally asks, what else is happening? One soothing way to approach it is to remember that Earth's climate is not a simple, linear machine. It's a system with memory, feedbacks, and thresholds. Sometimes it responds gradually. Sometimes it resists change until it reaches a tipping point, and then it shifts quickly. In a linear world, a small push produces a small movement every time. But Earth is not always linear. In Earth's climate, a small push can be absorbed, like pressure applied to a spring that doesn't move much yet. Or it can be amplified, like a small tap that begins a long chain reaction. The 100,000-year rhythm may not be a direct command from eccentricity. It may be an emergent tempo, a pattern that arises when orbital nudges interact with the slow growth and collapse of ice sheets, the brightness of the surface, the circulation of oceans, and the behavior of greenhouse gases. Think of it like a swing. If you push a swing gently at the right moment, each push builds on the last, and the swing grows higher. But if you push at the wrong time, you cancel the motion. The push itself may be small, but the timing makes it powerful. Now imagine the swing is enormous, heavy and slow, like an ice sheet that takes tens of thousands of years to build. The timing of orbital changes matters. The system can accumulate change slowly, storing it in the form of expanding ice, until it reaches a point where the next sequence of summers either allows it to keep growing or begins its collapse. So why specifically 100,000 years? There are several ideas, and none is the single final answer on its own. But together, they paint a plausible picture. One idea is modulation. Eccentricity changes how strongly precession affects seasonal sunlight. Precession, the wobble that shifts which part of the orbit lines up with which season, has a relatively short cycle, around 20,000 years or so. Precession can strongly affect whether northern summer occurs closer to the sun or farther away, which influences summer warmth. But the strength of precession's effect depends on eccentricity. If Earth's orbit is nearly circular, being closer or farther from the sun doesn't differ much, so precession's ability to amplify seasons is reduced. If Earth's orbit is more elongated, that distance difference becomes larger, and precession's seasonal impact becomes stronger. So eccentricity can act like a volume control for precession. It doesn't write the melody, but it can turn the melody up or down. During times of higher eccentricity, precession can create stronger seasonal contrasts, meaning the timing of northern summer relative to perihelion and aphelion matters more. During times of lower eccentricity, that effect softens. This doesn't automatically create ice ages on a 100,000-year schedule, but it helps explain why the climate might respond more dramatically in some eccentricity phases than others, making the long rhythm visible in the ice record. Another idea involves the behavior of ice sheets themselves. Ice sheets are not instant. They are slow to build and slow to remove, until they aren't. As they grow, they can become thick enough to change their own stability. A small ice cap is one thing. A massive continental ice sheet is another. A very large ice sheet can develop internal dynamics. It can flow under its own weight. It can interact with the bedrock beneath, and it can become vulnerable to rapid retreat once melting and calving accelerate. As ice sheets expand, they also press the Earth's crust downward. The land sinks under the weight. That changes the elevation profile and can affect how ice flows and how meltwater drains. The boundary between ice and ocean becomes especially important. When ice reaches the sea, it can break off as icebergs. That can speed up mass loss. So the geometry of the ice sheet, how far it spreads, how it meets coastlines, can shape how abruptly it can collapse. In this view, the 100,000-year pacing may arise because the system needs time to build an ice sheet large enough to become unstable in a particular way. The orbital cycles provide repeated nudges. Tilt and precession come and go. But the ice sheet, accumulating over many cycles, may only cross key thresholds occasionally, leading to large glacial terminations, spaced roughly by the time it takes to build that unstable mass. There is also a related hypothesis involving what lies beneath the ice. The nature of the ground, the sediments, and the friction at the base. Some researchers have proposed that changes in the condition of the bed, such as whether ice sits on hard rock or on deformable sediment, could influence how ice sheets grow and collapse. Over long periods, glaciers grind down the landscape, producing regolith and sediment. The interaction between basal sliding, meltwater, and sediments can affect ice flow speed. In that perspective, the ice sheet is not just responding to air temperature, it is interacting mechanically with the Earth beneath it, developing a kind of long-term evolution that could produce characteristic timescales. Another powerful assistant in this story, quiet but influential, is carbon dioxide. Ice cores show that CO2 tends to be lower during glacial periods and higher during interglacial warm periods. CO2 is not necessarily the initial trigger. It often follows changes initiated by orbital forcing and feedbacks. But once it changes, it can strongly amplify temperature shifts. A small cooling from reduced summer sunlight can allow ice to expand. Ice expansion and ocean changes can alter carbon storage, which can lower atmospheric CO2. Lower CO2 means less heat trapped, which increases cooling, which supports more ice. So orbital forcing can start the movement, and greenhouse gas feedback can strengthen it. This matters for the 100,000-year rhythm, because it offers a way for subtle orbital changes to produce larger climate responses. If the climate system is poised near a threshold, a small change in summer sunlight can set off a sequence. More ice, more reflectivity, ocean changes, lower CO2, more cooling, and so on. The result can be a large glaciation that looks disproportionate to the initial orbital push. And then comes the question of endings. One of the striking features of the Ice Age record is that glaciations often build slowly, but end relatively quickly, at least in geological terms. Ice sheets can grow over tens of thousands of years, but major deglaciations can happen over a much shorter span. This suggests that the system can accumulate tension, like a slowly bending branch, and then release it when conditions cross a threshold. A sequence of stronger northern summers, driven by alignment of tilt and precession, perhaps during a phase where eccentricity enhances seasonal contrast, can begin to melt ice. Once melting begins, the albedo feedback reverses direction. Less ice means a darker surface, which absorbs more sunlight, which causes more warming, which melts more ice. In addition, melting ice adds fresh water to the oceans, which can influence ocean circulation. Changes in circulation can alter how heat is distributed and how carbon is stored, which can influence atmospheric CO2, which can further amplify warming. So once deglaciation begins, it can accelerate. This helps explain why the climate record can show a slow climb into glacial conditions and a sharper exit. And it helps explain why the timing of large glacial terminations may not correspond simply to the biggest eccentricity peaks or the largest tilt changes. Instead, it may correspond to moments when multiple factors align and when the internal state of the ice sheets and the climate system is ready to shift. So the 100,000-year rhythm might be less like a metronome and more like a wave that rises when the system resonates. Another comforting way to picture it is to imagine the planet as having two favored modes in this period of Earth's history: a more glaciated mode and a warmer, interglacial mode. Orbital cycles gently push the system back and forth, but the system's internal feedbacks, ice reflectivity, ocean circulation, greenhouse gases, make it more likely to linger in one mode until enough nudging accumulates to shift it into the other. This can create a pattern where the climate stays cold for a long time, then flips into warmth, then gradually returns toward cold again. So when you look at the history of ice ages, you are not just watching the orbit. You are watching an interaction between orbit and Earth's own internal behavior, an ongoing conversation between space and sea, between sunlight and ice, between geometry and chemistry. And because these interactions involve thresholds, the climate can sometimes appear to choose the 100,000-year rhythm, even if the initial forcing at that timescale is not the strongest. It's as if eccentricity is not the hammer striking the bell, but the hand that steadies the bell at just the right angle, allowing other strikes, tilt and wobble, to ring out more powerfully at certain times. All of this can feel complex, but the essence can be held in a simple, sleepy image. Picture the northern summer as a warm lamp shining on a field of snow. Sometimes the lamp is slightly stronger, sometimes slightly weaker. Sometimes it shines a little longer. Sometimes it angles differently. Most years, the snow melts and the field darkens, absorbing more warmth next time. But during certain long spans of time, summer light is just a little too gentle, again and again. Snow remains. The field stays bright. The brightness reflects the lamp's warmth away. The snow survives even more easily. And slowly, patiently, the field turns into something else, a persistent ice world. Then, after a long accumulation, a new alignment arrives. Summer light strengthens. It lingers. It angles in a way that cuts deeper into the ice. Melt begins. The field darkens. Darkness absorbs the lamp. Absorption brings more melt, and the ice, which took so long to build, begins to retreat. So when we ask why the biggest cycles have often been about 100,000 years, we may be asking a question that has more than one answer. We may be seeing the combined effect of a slow orbital modulation that changes how strong seasonal timing effects can be, the long mechanical timescales of ice sheet growth and instability, feedbacks that amplify small changes into large ones, and thresholds that cause the system to resist, then shift. And it's okay in a sleep documentary to sit peacefully with the idea that nature can be both patterned and mysterious at once. Because the deeper truth is not that Earth is perfectly predictable like a clock. The deeper truth is that Earth is rhythmic, like a living thing. Rhythmic, but responsive. Repeating, but never identical. And in the far north, where land waits under long winters and brief summers, those rhythms matter intensely. A small change in summer sunlight can decide whether snow becomes a temporary visitor, or whether it becomes the beginning of a continent-sized memory. So as you breathe slowly, you might imagine those northern landscapes across deep time, the same rocks, the same broad plains, the same quiet shorelines, but with different coverings, sometimes green, sometimes brown, sometimes white. And the whiteness, when it arrives, does not arrive as a sudden conquest. It arrives as persistence, a winter that leaves snow, a summer that fails to remove it, a bright surface that reflects the next sunlight away, and a slow expansion that turns small remnants into glaciers, and glaciers into ice sheets, until the whole planet feels the weight of what began as a subtle seasonal imbalance. And above it all, the orbit continues, tilt and wobble continue, the geometry continues, calm, repeating, patient, like the slow turning of a story that has been told many times, in many ways, across Earth's long and quiet past. Now let's drift into the quieter forces, the ones that don't announce themselves loudly, but guide the climate like invisible hands. Because even if orbital cycles set the rhythm, changing how sunlight is distributed across seasons and latitudes, Earth's own systems decide how that rhythm is felt, whether it becomes a gentle cooling or a full global ice age, whether it fades away or deepens into tens of thousands of years of frozen time. To see how this happens, it helps to picture Earth not as separate pieces, ice over here, ocean over there, atmosphere above, but as one connected, circulating body. Heat moves, water moves, gases move, and small changes in one place can quietly echo into another. At the center of this chapter is something simple, but powerful. Earth's climate doesn't just respond to sunlight, it responds to sunlight plus feedbacks. A feedback is like an amplifier. It can make a small initial change grow larger, or it can dampen it, pushing things back toward balance. Ice ages are, in many ways, stories about feedbacks that reinforce cooling for long stretches, and then, at certain moments, flip direction and reinforce warming. One of the most important quiet assistants in this story is the ocean. The ocean is not just water, it is memory. It stores heat far more efficiently than air. It also stores carbon far more efficiently than air. It circulates slowly, mixing surface and deep layers, transporting warmth from place to place, and carrying dissolved gases into the darkness. If Earth's surface climate were only atmosphere, it might respond more quickly to changes in sunlight. But because the ocean is so large, so deep, and so slow, it gives the climate inertia. It smooths some changes and stretches others out over long spans of time. You can think of the ocean like a massive thermal battery. It charges and discharges slowly. When the climate begins to cool, perhaps because northern summers are mild and ice is beginning to survive, ocean temperatures shift too. Even slight shifts matter because temperature affects how gases dissolve in water. Cold water can hold more dissolved carbon dioxide than warm water. That's a simple physical fact. So as the ocean cools, it can absorb more CO2 from the atmosphere, lowering atmospheric CO2 levels. And CO2, of course, is a greenhouse gas. It traps heat, so here's the gentle loop. Cooling begins, perhaps modestly. Oceans cool. Cooler oceans can take up more CO2. Atmospheric CO2 drops. With less CO2 trapping heat, cooling strengthens. This is one way a small initial cooling can become a bigger one, not through a sudden leap, but through a quiet strengthening of the background. But this is only part of the story, because the ocean isn't a single uniform tank. It's layered, it's circulating. It has a surface that interacts quickly with the air, and a deep interior that can remain isolated for centuries or longer. So the way the ocean stores carbon depends not only on temperature, but on circulation, on the grand conveyor belt patterns that move water through the globe. When circulation changes, carbon storage changes. In the modern ocean, surface waters in certain regions become cold and dense enough to sink, carrying oxygen and carbon into the depths. Elsewhere, deep waters rise again, bringing stored carbon back toward the surface, where it can outgas into the air. During glacial periods, many scientists think the deep ocean becomes more effective at holding carbon, keeping it away from the atmosphere for longer stretches. The exact mechanisms are complex and can vary by region, but the basic idea is soothing in its clarity. The deep ocean becomes a stronger vault, and when the vault is stronger, less CO2 stays in the atmosphere. Less CO2 means a cooler world. cooler world means more ice, so the ocean can reinforce glaciation, not by freezing solid, but by shifting how it breathes carbon. Another quiet assistant is the ice itself, because once ice sheets exist, they don't just sit there like passive blankets. They reshape the planet's surface and behavior. First, they brighten it. Snow and ice reflect sunlight. We talked about albedo earlier, but here it becomes even more consequential. As ice spreads, the Earth becomes more reflective overall. More sunlight is bounced back to space. Less energy is absorbed at the surface. That encourages further cooling, which encourages further ice. This feedback is powerful because it directly changes how much solar energy the planet absorbs. Not the sunlight arriving at the top of the atmosphere, but the sunlight actually converted into warmth on the surface. Second, ice sheets change the shape of the world. A continental ice sheet can become kilometers thick. It is not just a surface feature, it is a mountain range made of ice. And a mountain range affects air movement. Wind doesn't flow the same way over a flat plain as it does over a giant dome of ice. Storm tracks can shift, moisture pathways can shift, the jet stream can bend and redirect. This matters because ice sheets grow from snowfall. They need moisture, so it becomes an intricate balance. As an ice sheet grows, it can alter the atmosphere in ways that change where snow falls. It can starve itself of moisture in some areas while feeding itself in others. The growth pattern can become uneven, with lobes and regions of faster advance, regions of slower flow, regions of thicker buildup. And beneath the ice sheet, something else begins to happen, something slow but important. The weight of ice presses down on the crust of the Earth. The land actually sinks under the load. This is called isostatic depression. Imagine placing a heavy book on a soft cushion. The cushion dips. Earth's crust behaves similarly, though far more slowly. As the land sinks, it can influence the stability of the ice sheet's edges. It can change how close the ice is to sea level, and how likely it is to interact with oceans. It can also change river patterns and the drainage of meltwater, subtly influencing how ice slides and flows. And when the ice melts away later, the land rebounds upward, a slow rising that can continue for thousands of years after the glaciers retreat. Even today, parts of Scandinavia and Canada are still rebounding from the last ice age. So ice sheets don't merely respond to climate, they bend the world, and that bending can feed back into their own behavior. Now, another quiet assistant enters the scene. Dust. Dust seems so small, a fine powder, a haze you might barely notice. But on a planetary scale, dust can matter in multiple ways, and during glacial periods, dust often becomes more abundant. Why? As climates cool and ice expands, many regions become drier. Sea levels fall, exposing continental shelves, new land that can become windy and dusty. Vegetation patterns shift, sometimes, leaving more bare ground. Winds can strengthen or change pathways. All of this can increase dust in the atmosphere. Dust influences climate by interacting with sunlight and with clouds. Depending on its properties, dust can reflect sunlight back to space, contributing to cooling. It can also absorb sunlight, warming certain layers of air. And it can help form cloud droplets or ice crystals, changing cloud behavior. But dust doesn't only affect the sky, it affects the ocean too. When dust settles into the ocean, it can carry nutrients, especially iron, which can stimulate the growth of certain phytoplankton in regions that are otherwise nutrient limited. More phytoplankton growth can draw down CO2 from the surface waters through photosynthesis, and some of that carbon can sink into the deep ocean when organisms die and sink, a process sometimes called the biological pump. So dust can, in some cases, encourage additional CO2 uptake by the ocean, contributing to lower atmospheric CO2 during glacial times. It's almost poetic. Dry winds lifting dust from cold continents, dust falling into the sea growing microscopic life helping to store carbon storage cooling the planet further. This is the kind of interconnection that makes ice ages feel like living systems rather than simple causes. Now add one more quiet assistant: sea ice. Sea ice is different from land ice. When sea ice forms, it floats. It doesn't directly raise or lower sea level, but it changes reflectivity and ocean atmosphere interaction in powerful ways. Sea ice is bright, like snow, so it increases albedo over the oceans. It also acts like a lid, reducing heat exchange between the relatively warmer ocean and the colder air above. This can influence weather patterns and help keep regions colder. Sea ice formation also affects ocean salinity. When seawater freezes, the ice contains little salt, and the salt is left behind in the surrounding water, making it saltier and denser. Dense water can sink, potentially influencing deep ocean circulation. So sea ice too can interact with the ocean's breathing and vault-like storage, affecting how heat and carbon are moved around. Now, if you step back and look at these assistants together, ocean circulation, CO2 feedbacks, dust, sea ice, the physical mass of ice sheets, you begin to see why orbital changes alone don't tell the whole story. Orbital changes set the initial pattern of sunlight, especially summer sunlight in key regions. But these internal processes decide whether that pattern becomes a dramatic climate shift. This also helps explain why ice ages can have a very particular feel in the geological record. They often build slowly, taking many thousands of years to deepen, but they can end relatively quickly, as if the system suddenly changed its mind. This asymmetry, slow build-up, faster collapse, can be understood through feedbacks that work in one direction for a long time, then flip direction. During glaciation, certain feedbacks reinforce cooling. Expanding ice increases albedo and cooling. Cooler oceans take up more CO2, reducing greenhouse warming. Changes in ocean circulation may store carbon more effectively in the deep sea. Dust and sea ice can further alter radiative balance and carbon cycling. These don't necessarily produce sudden changes. Instead, they can create persistence. They can keep the climate in a colder state for long stretches, even as orbital cycles continue to vary. Then, for deglaciation, a different set of conditions can appear. If northern summers become stronger, due to the alignment of orbital cycles, the ice begins to melt. Once melting begins, albedo decreases. Darker surfaces absorb more sunlight. That encourages more warming, which encourages more melt. At the same time, warming oceans can release CO2, and changes in circulation can bring deep stored carbon back toward the surface. Atmospheric CO2 rises. Greenhouse warming strengthens. That further supports melting. So the feedbacks that once reinforced cooling now reinforce warming. It's like a slow pendulum that spends a long time near one end, then swings more quickly to the other when conditions allow. Another subtle but important part of this story is that climate isn't only temperature, it's moisture patterns too. Ice sheets need snow, and snowfall depends on moisture carried by winds and storms. But as climates cool, colder air can hold less water vapor. This can reduce precipitation in some regions, potentially limiting ice sheet growth in certain ways. So glacial climates can be cold, but also dry in many places. Deserts can expand, dust can increase. These dryness patterns then feed back into dust dynamics and potentially into ocean fertility and carbon cycling. Everything loops. Even sea level enters the feedback web. When land ice grows, sea level falls because more water is stored on land as ice. When sea level falls, coastlines move outward. Continental shelves become exposed land. Ocean gateways can change. Shallow seas can become land bridges. And these changes can alter ocean circulation patterns and atmospheric circulation patterns. So the act of building ice changes the geometry of the planet in ways that can influence the climate that sustains that ice. And then, when ice melts and sea level rises again, the world rearranges back, flooding shelves, reopening shallow seas, restoring different patterns of currents. In this way, ice ages are not just cold times. They are periods where Earth's geography behaves differently. Now, you might be wondering, if these assistants are so strong, why doesn't Earth always fall into an ice age? Why doesn't it just spiral into freezing permanently? Because feedbacks can work both ways, and because the system depends on the balance between incoming sunlight, greenhouse gases, ocean circulation, and the current state of the planet. There are stabilizing influences too. Warmer conditions reduce ice, reducing albedo feedback in the cooling direction. Higher CO2 warms the planet, discouraging large ice accumulation. Ocean circulation can, at times, transport warmth to high latitudes, limiting ice growth. And of course, orbital configurations can favor warmer summers, limiting snow survival. So the Earth moves through its climates like a boat on a broad sea, sometimes pushed toward colder waters, sometimes warmed and turned back. The boat does not move because of one force, but because of many currents interacting. If you want a single calm image to hold all of this together, imagine Earth as an instrument. The orbital cycles pluck the strings lightly, changing sunlight distribution. But the instrument's body, ice, oceans, atmosphere, carbon, amplifies the sound. It resonates, it shapes the tone. It can make a small pluck echo loudly, or it can soften it. In some eras, the instrument resonates strongly with cooling, producing long glacial periods. In other eras, it resonates differently, producing different patterns. So when we talk about ice ages, we're really talking about a partnership. Space provides the rhythm of sunlight. Earth provides the response through its internal assistants, oceans, CO2, ice dynamics, dust, sea ice, and shifting geography. And perhaps the most soothing part of this story is how unhurried it is. None of these processes rush. Oceans take centuries to fully rearrange deep circulation patterns. Ice sheets take thousands of years to build. Carbon slowly transfers between air, sea, and living systems. Dust rises and falls with winds and dryness patterns. Sea ice expands and contracts with seasons, but its long-term presence depends on slow climatic shifts. This is climate as patience. This is a planet adjusting itself, continuously, in response to small changes in how sunlight falls, guided by feedbacks that can either deepen the cold or open the door to warmth. So as you listen, you might picture the Earth at night from space. A curved edge of blue atmosphere, thin as a whisper. Clouds spiraling gently over oceans. Ice shining softly at the poles. and deep below, the ocean carrying heat and carbon like a slow, silent river. And in that vast quiet, you can sense the assistance at work. The ocean holding carbon in its depths, the ice reflecting light back into darkness, dust drifting through air and settling into sea, sea ice spreading like a pale lid across the water, and the climate like a long story, turning page by page, not by sudden decisions, but by the cumulative effect of slow, connected motions. In this way, an ice age is not one event. It is an entire mood of the Earth, a state sustained by many quiet helpers, each reinforcing the others, until the balance shifts again and the planet gently begins to thaw. Settle into the final stretch of the story now. Not as an ending exactly, but as a widening of the view. Because when you look at ice ages from far enough away, far enough that centuries feel like seconds and millennia feel like minutes, you start to see that Earth's climate isn't a straight line. It's a rhythm, a slow, repeating movement, like a tide that comes in and goes out, but on a scale so vast that it reshapes continents. And in that rhythm, there is a strangely comforting idea. Earth has been here before. Not once, not twice, but many times, moving into colder worlds, then returning to warmer ones, again and again, while life adjusts, migrates, adapts, and continues. To understand where we are now, it helps to first imagine the pattern itself. Over the last million years or so, the planet has often spent long spans in colder conditions, glacial periods, interrupted by shorter, warmer intervals called interglacials. The cold periods can last tens of thousands of years. The warmer interglacials often feel like brief clearings in a long forest of ice. In glacial times, ice sheets spread across northern land. Sea level drops, sometimes by more than 100 meters. Coastlines shift outward. Entire shallow seas become land. What is now seabed becomes grassland and tundra. There were times when you could have walked across what is now the English Channel. Times when a wide land bridge connected Siberia and Alaska, allowing animals and later humans to move between continents. And then, during interglacials, the ice retreats. Sea level rises again. Coastlines move inward. The world's shape changes back. So even the geography we take for granted, where the ocean begins and land ends, has, in recent geological terms, been fluid. Now, let that image soften into something even calmer, a planet breathing. In a glacial phase, the breath draws in, ice expands, seas retreat, carbon shifts, dust rises. The world becomes brighter and colder in key regions. In an interglacial phase, the breath releases, ice shrinks, seas return, carbon rises, forests spread, warmth moves poleward. It's not a perfect heartbeat, it's not evenly spaced, but it is a rhythm. And when we say the last ice age, we're referring to the most recent major glacial period, which peaked roughly 20,000 years ago. At that peak, enormous ice sheets covered much of North America and Northern Europe. The landscapes would have been quiet and stark in many regions, dominated by ice, tundra, and cold winds. Then, as the planet began to receive stronger summer sunlight in the northern hemisphere, and as feedbacks shifted direction, the ice started to retreat. Meltwater poured into the seas, sea levels rose, the climate warmed into the interglacial we live in today. This warm period is called the Holocene, and it began roughly 11 or 12,000 years ago. In the broad sweep of Earth history, it is very recent, so recent that most of human civilization has unfolded within it. Agriculture, cities, written language, industry, modern technology. All of it has happened during this relatively stable warm interval. And that stability is part of why the question feels so intriguing. If Earth naturally enters and exits ice ages, what does that mean for us now? To approach that gently, it helps to separate two different ideas. One is the natural rhythm of orbital cycles and climate feedbacks. The other is the current human influence, especially greenhouse gas emissions, on the atmosphere. In purely orbital terms, Earth's current configuration does not suggest we are at the most intense northern summer sunlight compared with many times in the past. In other words, we are not at a peak of maximum melt power for northern ice sheets driven by orbital geometry alone. In some previous eras, configurations like ours might have been associated with a long, gradual drift toward cooler conditions over many thousands of years. But orbital cycles operate slowly. Their changes unfold over tens of thousands of years. They are like the long, slow turning of a wheel. And our present situation includes something much faster, a sharp rise in greenhouse gases, especially carbon dioxide, over the last couple of centuries. This matters because greenhouse gases shift the baseline of the climate system. If orbital cycles are the rhythm that gently nudges the climate back and forth, greenhouse gases are like the thickness of the blanket around the planet. A thicker blanket means the Earth retains more heat. That retained heat changes how easily ice can form, how readily snow survives summer, and how the oceans and atmosphere exchange energy. So even if the orbital rhythm were to nudge toward cooling over the next many thousands of years, a warmer baseline can weaken that nudge, perhaps delaying, perhaps preventing the kind of long-term snow survival that allows major ice sheets to grow. But it's important to hold this in a calm, time-stretched way. We are not talking about next winter, or next decade, or even the next century as an orbital ice age schedule. The orbital rhythm is not a countdown timer. It is a slow drift in the pattern of sunlight. In the natural system, ice ages require long spans of repeated summer conditions that favor snow survival in key regions. That takes time. It takes accumulation. It takes thresholds. It takes the cooperation of feedbacks. So when people ask, are we due for an ice age? The most honest answer is that Earth's climate doesn't work like due dates. It works like a complex instrument responding to multiple influences. And right now, a strong influence is pushing toward warmth rather than toward glacial buildup. But beyond the modern question, there's a deeper, more timeless insight in this final part of the story. Ice ages are reminders that Earth's climate is capable of large change, even without human involvement. The idea that climate should be fixed is a human illusion born from short lifetimes. Earth's normal is variability. The planet's history is full of shifting climates, shifting oceans, shifting ice. And yet, within that variability, there is order. The orbital cycles provide a kind of structure, like a slow metronome in the background. They don't dictate every detail, but they keep time. When you look at the pattern of glacial cycles, you start to recognize the interplay of slow and fast. Slow orbital nudges build conditions over many thousands of years. Feedbacks amplify changes and create long persistence. Thresholds allow sudden-looking shifts when the system crosses a line. So the story becomes one of gradual preparation and occasional release, like the slow building of pressure and the sudden opening of a valve. This also explains why the end of an ice age can feel sudden. Once a large ice sheet begins retreating, the world darkens. Darker land and water absorb more sunlight. More absorption means more warming. More warming means faster melting. And the melting itself adds water to oceans, changes circulation, and can encourage greenhouse gas increases, reinforcing the transition. So the planet can, in a relatively short span, move from a deep glacial world to a warmer one, like a long winter breaking into spring. Now, consider what an interglacial world like ours really is. It is not merely normal, it is a special window in a longer pattern. During interglacials, forests often extend farther north. Grasslands shift. Deserts may expand or shrink depending on regional patterns. Sea levels are higher. Coastal ecosystems exist where they can only exist in warm periods. This is why the Holocene has been such a fertile period for human settlement. Stable coastlines in human terms, reliable seasons, again in human terms, and a climate that supported agriculture. But even the Holocene hasn't been perfectly stable. There have been regional shifts, droughts, cold intervals, and warm intervals. Climate is always moving. It's just that, compared with glacial times, the Holocene has been a calmer surface on the ocean of time. And now, in the last 2 centuries, that calm surface has been disturbed by rapid warming. Here, it can be soothing to remember that the Earth system will continue regardless. What changes is the kind of world it becomes, how quickly it changes, and what that means for societies and ecosystems that evolved under certain expectations. Ice ages teach us that life is adaptable, but they also remind us that adaptation takes time. Ecosystems migrate slowly. Species respond over generations. Shorelines change slowly in natural cycles. Rapid changes compress those adjustment timescales. They make transitions harder. But again, in this sleep-focused story, it's enough to hold the long view. Earth responds to the forces acting on it. Always has, always will. And the orbital cycles, the slow geometry of Earth's motion, will keep turning in the background for as long as the planet remains. So where does that leave us right now in the grand rhythm? We live in a warm interglacial with relatively small remaining ice sheets compared to glacial maxima. Greenland and Antarctica still hold vast ice stores, but the great continental ice sheets that once covered Canada and northern Europe are gone. Sea level is comparatively high. The planet's surface is relatively dark in northern mid-latitudes compared to glacial times, meaning it absorbs more solar energy than it would under an expanded ice cover. In a purely natural rhythm, Earth might eventually drift toward conditions that could support glaciation again, given enough time and the right alignments and feedbacks. But that eventually is measured in many thousands of years, and the path is not predetermined. It depends on greenhouse gas levels, on ocean circulation, on the state of ice sheets, on feedbacks that can amplify or damp changes. In other words, the future is not a single track. It is a landscape of possibilities shaped by the forces at play. And maybe the most calming way to end is to return to the image of Earth breathing. The planet has its slow inhale and exhale through ice and warmth. It has its internal assistants, oceans storing heat and carbon, ice reflecting light, dust drifting, currents shifting. And it has its external rhythm, tilt, wobble, orbit, quietly rearranging sunlight. If you imagine standing at the shoreline of deep time, you can almost hear it, the slow advance of ice, like a far-off hush, the retreat, like meltwater finding its way back to the sea, the coastline moving in and out with sea level, like a tide too slow for any human to watch directly. And within that vast motion, human life appears as a very brief flicker, important to us, of course, because we live inside it, but brief compared to the cycles that shaped the planet long before us. That perspective can feel humbling, but it can also feel comforting, because it reminds you that the world is not chaotic in a meaningless way. It is patterned, it is interconnected, it is responsive. The same physical laws that guide snowflakes, oceans, and sunlight have guided the planet through countless changes, and the planet has carried life through those changes in many forms, adapting, evolving, shifting. So if your mind is still curious, still wondering why ice ages come and go, why the planet seems to breathe in cold and out in warmth, remember that you've already encountered the key idea. Small changes in sunlight distribution can, through feedbacks, become large changes in climate. And those large changes reshape the world, then fade, then return in slow rhythms. Now, take a slow breath in and let it out gently. Imagine Earth turning quietly in space, blue and white, with soft clouds drifting over dark oceans. Imagine the poles shining faintly. Imagine the seasons moving like a calm wheel. And in the far background, beyond any single lifetime, imagine the slow orbital dance continuing. Tilt, wobble, shape of the orbit, guiding the gentle distribution of sunlight, guiding the long climate rhythm, guiding the planet through its ancient, patient cycles. And as you rest, you don't need to solve the entire mystery tonight. You can simply let the story hold you. A world that breathes, a world that remembers, a world that changes slowly, and a quiet rhythm of light and ice, repeating over and over through time.